Now that we've learned how an equilibrium forms, we'll apply those same concepts to acids and bases. You've learned in the past that the definition of an acid was something that caused the hydrogen ion concentration in water to increase. That's the Arrhenius definition of an acid. And the Arrhenius definition of a base is a substance that, when it's dissolved in water, increases the concentration of hydroxide ions. The Arrhenius definition of an acid and base limits us to just aqueous solutions. But the Bronsted-Lowry definition is a little bit more broad, an acid being a proton donor and a base being a proton acceptor. And as a Bronsted-Lowry acid, it must have a removable or acidic proton. So hydrogen chloride gas then is a Bronsted-Lowry acid because in the presence of water, it's highly soluble, and so it will ionize, forming hydrogen and chloride ions. Water could be an example of a Bronsted-Lowry base. An example of a Bronsted-Lowry base is one that has a pair of non-bonding electrons. And here's a water molecule with two pairs of non-bonding electrons. And so by accepting a proton from HCl, it's behaving as a base. Remember that when we express the hydrogen ion like this, that is the equivalent of this, a hydronium ion. So when we say that we have hydrogen chloride gas, if we write it a little bit differently with water, the whole reason that HCl ionizes so completely is because A, it's a really polar molecule, and B, it's being dissolved in a very polar solvent. And so what ends up being formed is that if we have our Bronsted-Lowry base here, acting as a hydrogen ion acceptor, then what's being formed is a hydronium ion, which we usually express more simply as H plus, or a hydrogen ion. And so we have our Bronsted-Lowry acid donating its proton to our Bronsted-Lowry base, our proton acceptor. And by the way, what's left is this chloride ion on the product side. Some species have unshared pairs of electrons and ionizable hydrogens, which makes them able to behave as an acid or a base. The term we use for species that can behave as an acid or a base is amphiprotic or amphoteric. Hydrogen chloride is a Bronsted-Lowry acid because it has an ionizable hydrogen. Water is amphoteric or amphiprotic and be an acid or a base. But when dissolving hydrogen chloride, it's going to behave as a Bronsted-Lowry base. It's got two unshared pairs of electrons on the oxygen that will attract the hydrogen away from the hydrogen chloride. When the hydrogen moves over to the water molecule, it forms a hydronium ion, often expressed as just a hydrogen ion, H+. And what's left is known as the conjugate base of this acid, or the chloride ion. Acid-base reactions are always going to result in the formation of conjugate pairs. Here we have nitric acid. It's going to lose its hydrogen ion, and what will be left will be a nitrite ion. And so the species that's formed once the hydrogen ion has been donated from the acid is called its conjugate base. So the nitrite ion is the conjugate base of the acid nitric acid. In this reaction, water is acting as the base because it's accepting the hydrogen ion, forming hydronium ions. And so because it's a base, as a reactant, it's a base accepting hydrogen ions, the new substance that's formed, the new species that formed, the hydronium ion, would be its conjugate acid. Strong acids are considered strong because they completely dissociate in water. HCl we know to be a strong acid, and so it's going to ionize very easily. And so its conjugate base, the chloride ion, since this ionizes so easily, the chance of chloride ions turning around and trying to pull some of those hydrogen ions back to it is very, very slim. And so the relative strength of a conjugate is going to be as such. The stronger the acid, the weaker its conjugate base. So chloride ions in a reaction are always going to be spectators because HCl is such a strong acid. As a conjugate base, the effect of chloride ions in the solution is going to be negligible. Water is a pretty weak acid. We know that it can donate one of its hydrogens, but it doesn't do so very readily. When it does, its conjugate base it forms is a hydroxide ion. And we know that hydroxide ions do have a pretty strong affinity for pulling back hydrogen ions. And so while water is going to be a weak acid, it's not very readily going to give up a hydrogen ion. Its conjugate base, the hydroxide ion, is going to be somewhat stronger in terms of being a base because it will attract hydrogen ions to it. So remember, the stronger the acid or base, the weaker its conjugate. There are some substances that contain hydrogen that do not dissociate in water, and so they have very negligible acidity as such. Their conjugate bases are going to be very, very strong. In acid-base reactions, the equilibrium is always going to favor the reaction that's going to move the proton towards the stronger base. And since we know that the chloride ion is the conjugate base of a strong acid, it's then a very weak base. And so water is a much stronger base than the chloride ion. And so this reaction is going to go fully toward the product side. So far, in fact, that if we calculated a value for K, the number would be huge because at equilibrium, there really isn't an equilibrium because it goes all the way toward the product side. And so we would have nothing of our HCl unionized in this reaction. And for that reason, when we have a strong acid, we won't assign a value of K to it because it's infinite. Here we have acetic acid and water. Acetic acid is a weak acid, and so it's only going to partially ionize, and it will form an equilibrium. And so at equilibrium, all of these species will be present in some amount. And since acetic acid is a weak acid, that means its conjugate base, the acetate ion, is going to be a somewhat stronger base. Since acetate's the stronger base, equilibrium is going to favor this side of the equation. So then when an equilibrium forms, we're going to have more of our reactant present than we would have product. So our value for K then is going to be smaller, relatively. So a small value for K means we have a weak acid, where a large value for K means we have a relatively stronger acid. So we've said that water is amphoteric or amphiprotic, meaning that it can act as an acid or a base. So in pure water, some of the water molecules are going to react with each other as they're bumping around and bouncing off of each other. And when they do, what happens is that we form, every now and again, a hydrogen ion will come off of one water molecule and go and bond to a neighboring water molecule, forming a hydronium ion, where the water molecule has taken on the hydrogen, acting as a base, and leaving hydroxide ions where the water has acted as an acid. And so this process is referred to as the autoionization of water. And this in and of itself is an equilibrium process. If we're to write an equilibrium expression for the autoionization of water, it would look like this, omitting the water in its liquid form. This constant is known as the ion product constant for water, and we give it a special label, Kw. And at 25 degrees Celsius, the Kw, ion product constant for water, is 1 times 10 to the negative 14th. We can use the ion product constant for water to determine the pH of a solution. pH, by definition, is the negative log of the hydronium ion concentration, or the hydrogen ion concentration. In pure water, since the Kw is 1 times 10 to the negative 14th, and that is the product of the hydrogen and hydroxide ion concentrations, then we can determine what the hydrogen ion concentration would be by taking the square root of that number, and we would get 1 times 10 to the negative 7th. And since the negative log of 1 times 10 to the negative 7th is 7, then we know that in pure water the pH is going to be 7. And so anytime we have more hydrogen or hydronium ions than pure water, we know we're going to have an acidic solution, and our pH then would be less than 7. If we have a lower hydronium or hydrogen ion concentration than what we would have in pure water, then we have a base. And in that instance, then we'll have a pH that's greater than 7. Some pH values for some common substances. We know we have HCl in our gastric juices, and so we have a hydrogen ion concentration, or a molarity, since it's a strong acid, of around 0.1 molar and a pH of 1. And so then lemon juice with a pH of 2, still pretty acidic. And then we move into the more neutral territory of milk, saliva, human secretions, into the neutral area here. And then in the more basic, you can see bases tend to be slippery and slimy and used for cleaning. And so bleach and ammonia are examples of fairly strong bases with high pHs, and sodium hydroxide or lye, drain cleaner, is another very alkaline substance. So we've learned that we get pH is equal to the negative log of the hydrogen or hydronium ion concentration. We have some other P scales that work very similarly. For example, we have pOH, which we would find by calculating the negative log of the hydroxide ion concentration. Or we could also use pKw, which is the negative log of the ion product constant for water. And so we can take all of these relationships and put them together like this. If we know that the product of the concentration of hydrogen or hydronium ions and hydroxide ions, or the Kw, is equal to 1 times 10 to the negative 14th, and we know that the negative log of the hydronium ion concentrations plus the negative log of the hydroxide ion concentrations equals the negative log of the Kw, is 14, then we could substitute the pH plus the pOH is equal to the pKw, or 14. This is how we use the pH scale as being on a scale of 0 to 14. The values for pH and pOH will add up to a total of 14. When we get into the lab, we'll be measuring pH with a pH probe. There's other ways that we can measure pH. We can use litmus paper. We can also use Hydrogen or pH paper, or we can use indicators. And these are some indicators that are frequently used in biology and chemistry, and they're effective pH ranges for where the colors will change. This is similar to the type of pH probe that we'll be using in the lab. And that's it for now.